So we're going to make another assumption about we're going to make a similar assumption. We're going to assume that the function f of x is constant on each subinterval, but we're going to use the midpoint of each interval. Now, this is going to restrict us because between 0 and 5, we don't know what's going on at the midpoint. So in this case, we're going to have to use wider intervals so that we can actually have a midpoint as part of our data set. So in this case, we will need to use wider intervals so that each interval has a midpoint. We have a value for the function that's at the midpoint. So I can't do delta x equals 5 because I don't know what's going on at the midpoint of this interval. But if I expand my delta x to be 10 and just use 2 subintervals, if I go n equals 2 intervals with a delta x of 10, then I do have a midpoint. There's a midpoint of the first interval, and there's a midpoint of the second interval. The idea is that we only get to use the data that we actually have. I can't speculate some midpoint between 10 and 25. I can't just take the average of those two things because that's the trapezoidal rule. And that assumes a particular kind of concavity. So we're going to drop down from 4 intervals to 2 intervals and use the midpoint. So what that would look like, instead of delta x being 5, I'm just going to break this into 2 intervals. And I'm going to use the midpoint, 25, for this whole first 10 units. And so that is going to be my first rectangle. It's a rectangle because we're still assuming the function is constant. But we're only doing 2 rectangles. The advantage here is that a midpoint, if a function is unidirectional, if the function is always increasing or decreasing, monotone is the actual word for it. If a function is monotone, then we'll have some overestimate here, but we'll have some underestimate on the other side. If the function was decreasing, then the overestimate, and that's still increasing. If the function was decreasing, then our overestimate and underestimate would just be on the other sides. So I'm only going to use 2 subintervals, so my midpoint rule the midpoint rule is going to be, I'm going to use 25 for the first midpoint, but my delta x is now 10. And then my next rectangle has a midpoint of 40, but my delta x is 10. So one of the advantages that this rule has is that we are making fewer calculations. So if I do 25, I just want 25 plus 40 times 10, so that'll be 650. That's the midpoint approximation. Any questions? Here's the interesting thing about the midpoint approximation. The midpoint approximation, if the midpoint approximation is an overestimate, when the trapezoidal approximation is an underestimate, and the other way around. So the midpoint rule is, we could, the one on the other side we could think of would be the trapezoidal rule. So left and right are on either side, midpoint and trapezoid are on the other side. If we did the trapezoidal rule for 2 subintervals, let's see, our delta x is 10, we have to divide it by 2 because of the trapezoidal rule, because of the average. And I would use the first entry. Oh, it would be 10. We would use the middle entry, 35, twice. And then the last entry once. So let's do this is the trapezoidal rule with 2 subintervals. Let's find out what that's going to be. So I've got 10 over 2, which is just 5. And I have 10, 2 times 35, and 42. So with 2 intervals, we can say the actual value of the definite integral is more than 610 and less than 650. So the actual value from 0 to 20 of f of x to x will be less than 650 and more than 610. So there's a 40 point range between those two. If we this is better, even with only 2 subintervals. This is better than the difference we had between the left and right. The left and right endpoint approximations were 550 and 710 when we used 4 subintervals. So there's a difference of over 100, of 160 between the left and right. So with 4 subintervals, with all these calculations that we had to do, we were within 160 of the actual value. But with much fewer calculation, with only 2 subintervals, now we've got our actual value within 40. Any questions? So this is a better, we've narrowed it down even though we've used fewer subintervals. Because down here we have, this is trap 2 and mid 2. Whereas before, even with 4 subintervals, we had this between 710 and 550. That was with twice as many intervals. This was left 4, and 710 was right 4. So we have a better approximation with fewer intervals.
Can I ask a question?
Uh-huh.
So since when we did the trap 4 versus the trap 2, so the trap 4 is still more accurate than the trap 2 though, correct? So the 630 is more accurate than the 610?
Yes.
Okay.
But when we want to create bounds for the actual value, we have to use the same number of subintervals. Any questions? So we got a better approximation with fewer intervals. Since the midpoint rule and the trapezoidal rule will over and underestimate the actual value, it occurs to us that we might want to average those two. And we do, but we don't want to give each one the same weight. So to average the midpoint rule and the trapezoidal rule, we use what's called Simpson's rule. To average the midpoint rule and the trapezoidal rule approximations, we use Simpson's rule. So when Simpson was doing work on this, No relation to the family in the TV show that I know of. Actually, I don't even know this person's first name. When Simpson was first working with these approximations, they noticed that the midpoint rule and the trapezoidal rule were always on opposite sides of the actual value, and that the midpoint rule was usually twice as close. So if the trapezoidal rule was within 10, the midpoint rule would be within 5, roughly. And so Simpson had the idea, what if we find the average of these but don't weight them evenly since the midpoint rule tended to be closer? Let's give the midpoint rule 2 and the trapezoidal rule 1. So we're going to find a weighted average of 2 midpoint rules and 1 trapezoidal rule. So Simpson's rule is a weighted average of 2 midpoint rules and 1 trapezoidal rule. So there's 3 things: the midpoint rule, and the trapezoidal rule. So the Simpson's rule, simp n, is going to be 2 mids and 1 trap divided by 3. So in the case of our function here, 650 and 610, I wouldn't average these to land at 630. I would count the midpoint rule twice and the trapezoidal rule once. The midpoint rule gets a bigger share. So if we do, let's see, parentheses, 2 midpoint rules plus 1 trapezoidal rule and divide by 3. So we get 636.7, so 637, we call it. Any questions? Last thing about Simpson's rule, the assumption that we're making when we do this approximation is that the function is quadratic on each subinterval. So left, right, and mid are all assumptions that the function is constant on each subinterval. The trapezoidal rule is assuming that the function is linear on each subinterval. Simpson's rule is assuming that the function is quadratic on each subinterval. So just taking these 2 points and making a quadratic function connecting them. Then take the next 2 points and make a quadratic function connecting them. Oops. Any questions? Comments? Or snide remarks? All right, let's pause the video here. Talk about next steps.